evening, everybody. Welcome to tonight's edition of the Triangle Area SQL Server User Group's Advanced DBA subgroup. Tonight we have with us special guest Bob Pusateri, who's going to talk to us about SQL Server data compression, going a little bit deeper than you normally would see with compression. So please, Bob, take it away.
All right. Thank you very much, Kevin. Thank you all so much for showing up tonight. Thanks for having me. This is SQL Server Data Compression, the deeper dive. Just to briefly introduce myself, my name is Bob Pusateri. I am out of Chicago. Been working with SQL Server for about 20 years, the last 15 or so actually as part of a paid job. I'm a friend of Redgate and MVP, a Microsoft Certified Master, which generally means that if I have that certification and $2.50, I can ride the subway in Chicago. I used to run some of the users groups in Chicago. Also help organize the Saturday SQL Server and data platform events that take place there, and hopefully we'll get back to those soon. Probably the best thing on this slide is my contact information. So if you have questions that we can't get to, or if you're watching a video of this later and want to reach out, Twitter or my email there are the absolute best ways to get in touch with me, and I will have all this information again at the last slide at the end. So you'll get it there. Just to head off the question that usually comes up pretty quick, all this material, the slides, the demo database, the demo notebooks, all the resources I link to, everything will be available to download. I will have the link for that at the end. So if you'd like to follow along or try this yourself, that will not be a problem. All right, so our agenda for this evening, we're going to just talk about some very basics of compression real quickly, do a little primer on different types of compression and how that works. We'll talk about the SQL Server row and page compression features that were introduced in 2008, and then we'll dive a little bit into Columnstore as well and see kind of how that works, how compression internals work for Columnstore, and we'll take some questions kind of in between each point, and then again at the end. So why are we compressing data? Just to very briefly start off, disk space is cheap. You can get, hard drives relatively cheap at your local big box electronics store these days. 12 terabytes, probably bigger than that, even if you're looking. And if you're really hardcore, you're on like those data hoarder groups on Reddit where they talk about how to shuck these drives and jump the pins and do all kinds of stuff and get your storage for cheaper, right? Disk space is pretty cheap these days. It's only getting cheaper, but unfortunately, if this is a mission critical system, we need enterprise disk space, which is not nearly as cheap, right? It costs more because it's built better. You also have to generally pay for some sort of support, but then you get, the ability to have stuff replaced generally rather quickly, better warranties, etc. So yeah, disk space is cheap. Enterprise disk space, not so much. Another reason we might need to compress is maintenance, right? So if we have a large database or even not a large database, we need to do all kinds of maintenance on our data, right? A lot of these maintenance tasks are size of data operations, right? If we're doing something like a DBCC check DB, we need to read through literally every page in the database. So if we are deploying compression within our database, well, that means we can store more data on fewer pages, which will help make some of these maintenance processes faster just by virtue of having less data to read. Also, memory, right? Memory is still more expensive than disk. Memory, of course, has come down in price like disks have, but generally memory costs more. Um, if we're using compression in our database, well, we will be able to store more data in memory as well, which means we'll have to go to disk less, which can definitely lead to increased performance. And if you're curious about this picture, this is hand woven ferrite core memory. This is a total of 18 bytes you're looking at on your screen. That would have taken up about 2 by 3 inches, supposedly, is what the caption from this photo said. Another reason to compress is I/O, right? I/O is a bottleneck in a lot of systems and still can be today, even though we have super fast storage arrays and SSDs and things that are just blindingly fast. Usually there's a bottleneck somewhere in the I/O subsystem. A lot of times, between the actual super fast appliance and the machine that's running the database instance. There's a lot of different in between levels there where stuff can get bottlenecked, and unfortunately, this will show itself as the storage subsystem slowing down your system. So if you have compression, you can go to I/O system less and not have to worry about it. Not have to worry about that aspect of what's slowing you down as much, at least. Now, to talk about different types of compression that exist, there's two major families of compression. There's lossy compression, which is where we're actually changing and getting rid of some of the details of the data that we don't need anymore, right? So we have, images are generally lossy compression. So you could use a JPEG or the new HEIC, high efficiency image compression formats. These will get rid of some of the data. Um, Hopefully an amount that you can't really notice the difference, but that's one way that they're saving you space is by actually throwing some of that data away. Or, audio compression, like the old school WIMAP here, right, where we can talk about assaulting barnyard animals. We have MP3s, we have AAC compression, AC3. These are all lossy audio compression codecs that will get rid of some of the details of what you're listening to. Again, hopefully a degree that you're not aware, but it is changing what's being stored and reducing it and then compressing that. And we can do the same thing, of course, with video, with all the streaming services we know and love. Lots of different video codecs out there, especially now, H.264, H.265. There's a H.266 that was approved as a standard not too long ago. Great video compression, but these are all lossy formats. Lossy is great for things like this where we can tolerate some of our data going away. But when we're talking about databases, that isn't a good idea, right? I don't want to lose data or change the data to a degree that I can't get back exactly what I had before, right? So for data, we really need lossless compression, right? We don't want that data to change. And there are, of course, many lossless compression methods as well. Probably the simplest, just to touch on very briefly, is known as Huffman coding. This was actually an academic paper from, I believe, the early 1960s, talking about just simply analyzing the data, figuring out what patterns are most frequently repeated, and then taking the most frequently repeated patterns and representing them in some sort of lookup coding table with a small number of bytes. And the more frequent something is repeated, the fewer number of bytes you need to call up that value, with the idea being that you can achieve savings in that matter. We have lots of other compression codecs, of course, that involve different forms of statistical modeling. We're not going to get into exactly how these work because they don't matter for us, but there's a whole bunch out there. Generally, they all do some sort of modeling. We'll create a dictionary of most common patterns and then reference them with some sort of pointer where appropriate, thereby saving you space. Um, and this is for zip files, even Microsoft Office files, the formats that were introduced back in 2007, 2008, whatever, like XLSX, the Office XML files. Those are all actually zip files behind the scenes. That's compressed too now. So you have lots of different methods where compression is present in your daily life, usually even lossless compression where you don't know it, but it's generally there. So to kind of take these cases I've brought now and bring it into SQL Server, we need to compress the database. Why don't we just zip the SQL Server database file, right? Take master MDF and make it master.zip and call it a day, right? Well, that wouldn't really work so well. These methods are great for big amounts of data, and you absolutely could zip the MDF file, but then you'd have to unzip the entire file to be able to read it. And that'd be terrible because that's not how a database works, right? Database I/O is usually pretty random. It's reading different pages and extents from around the file in a fairly random fashion, unless you happen to be scanning something in order. And generally, it's small. Like I said, we're reading 8 KB pages, 64 kilobyte extents. Compressing the whole file at once like this isn't really going to help us. So we need to balance the compression ratio we can achieve, the amount of space we save, and speed, right? If we're compressing something and getting really good compression out of it and it affects the performance of our database, well, why bother, right? We needed something, or Microsoft rather, when they were designing data compression, they really needed compression that was pretty good, but that would not affect performance at all. And that's really what they came up with, and we'll dive into the why and how they did that very shortly here. To talk about where that data compression occurs in SQL Server, and again, this is the row and the page compression that I'm mentioning first here. Let's have a very simplified model of our database system, right? We have data on disk, we have memory, we have the what's called the access methods, which is how SQL Server actually takes the data in memory and translates it into rows and columns that would be represented to a user, and that is what's presented to the user, right? What happens is the compression actually occurs in those access methods. And what this means is that the data is compressed both in memory and on disk, right? So you not only save the amount of space you need on disk because you can store more data in the same amount of disk space, but you can store more data in the same amount of memory as well, right? That's a great advantage, right? I have more data in memory. I don't need to read from disk as much. That helps my performance even more. The downside is the uncompressed data is never cached anywhere. So if you have to read the same row from a table 10,000 times, well, you're going to be decompressing that same data 10,000 times as well. There is absolutely no caching of uncompressed data when you're using compression in SQL Server. So to talk about the compression types very briefly, or not briefly, but just to show them and what is probably the most impressive PowerPoint animation I've ever done, we have what's called row compression, there's page compression, and then finally we'll talk later about column store. So with that, let's dive in and actually discuss how row compression works in SQL Server. And the term compression for row compression is kind of overselling it. It does a great job. It does important work, but it's really not compression. It's more of a storage optimization than anything else. But the result is compression. So the idea with row compression is you're only using the space you need, and it does this by taking fixed length numeric data and making it variable length. So it only needs the amount of bytes necessary to store that value. So if I have a column of type int, right, that would normally be 4 bytes per value we're storing in an int column. But if I'm storing the value 5, I don't need 4 bytes to store the value 5. I can do that in 1 byte, right? So that's exactly what row compression would do. Is row compression would say, yeah, this is a 4-byte int, but we're only going to represent it as 1 byte with this compression. We're shaving off those other 3 that we don't need to represent this value. Does the same thing with character data. If it's a fixed length character type, like char 100 here, as I have on the slide, and you're only storing something that's 3 characters long, well, normally it would take up 100 characters in memory and on disk, but with row compression, it will only take up what it needs, so 3. If you have 0 values or null values, those take absolutely no space at all, which is pretty awesome. And then if you have a variable length columns, like varchar or whatever, there's a new record structure for those, so you get some overhead reductions there as well. Typically, it would take 2 bytes per column per variable length type to actually store the length of what is being stored in the variable length. So if you had varchar 300 and you had something that was 5 bytes long, it would actually take up a total of 7 bytes on disk. It would take the 5 bytes you need to store it and 2 bytes to store the fact that it's only 5 bytes long. But with row compression, this got optimized a little bit, and now you're only using 4 bits per column instead of 2 bytes. Right, and this is for variable length columns of less than 8 bytes. And this is done with what are called column descriptors. So now we're storing on a per row basis a record of what is in these columns and what their lengths are and what they need to be translated to at the end before being presented to the user. Okay, this gives you more than anything row compression. As I said, it's an optimization. It will give you protection from poor data typing, right? If you work in a shop where all values must be big int, whether they should be or not, well, if you turn on row compression, you'll save yourself the wasted space for the plenty of those values which probably don't need all 8 bytes of storage for that particular case. Row compression does not affect the smallest date types. So if you have like tiny int, the smallest integer type, or small date time, or date or time, the smallest of those date types, row compression will not change them. Those can't be changed. If you use the bit data type just to store a binary value, the way that works is without compression. If you create a column in your table of type bit, it is actually setting aside 8 bits. Um, just because the smallest it can allocate is 1 byte. So it's setting aside 8 bits and the other 7 are unused. But if you create another bit column on that table later, it'll use that same pool of space to store that value as well. With compression, that'll be shrunk to 4, so you get a little overhead savings there. And if you have Unicode data, it might be compressed. It's going to use what's called the standard compression scheme for Unicode algorithm to try to compress it. It's actually going to be kind of smart about it, and it's going to determine, hey, can I see a compression advantage with these values? If I can, well, great, we'll use it. If not, then won't waste the time. And if it's nvarchar max, it will not be compressed at all. So to kind of take everything I told you here and to put it a little more graphically to help hammer it home, I have I'm going to call it a table with two columns, right? It's got an ID column of type small int, which is 2 bytes, and it's got a first name column of char8, which is 8 bytes, whether those bytes are used or not, right? So I got 3 rows here, and I've got an ID number and a name. If I were to deploy row compression to this now, here's how it would change. First of all, it would take the ID values, and if they did not need both bytes to store that value, well, then it would only use one instead of two, right? So for the first record there for Sam's ID number of 92, well, that doesn't need 2 bytes. You can store 92 in 1 byte, so it will. It will then take the name Sam, stick it right after that, and all the other empty space can be reclaimed and used for other rows. Same for Nick. Nick can see some savings as well in the name, but not in the ID. And then Michelle sees savings in the ID and then 1 byte on the name, right? So we get some pretty decent savings out of this. We get a 60% savings for the first row, 40% for the second row. Third row is 10%. So there is no more fixed width in this data structure now. Now, one of the advantages of fixed width is SQL Server always knew, if it's reading this table, well, if I need to read the name column, I just skip the first 2 bytes, right? And then will be exactly where the name starts. Now it doesn't know where the name is going to start because it might start at the second byte, it might start at the third byte, it might start at 0, depending on if that ID is null or not. So it has to read that column descriptors to determine where is it actually going to start reading these values. But with these space savings and the fact that the CPU operations for this are fairly trivial, you'll usually always come out on top. So with that, I'm going to skip ahead, or not skip ahead, but rather transition us to some demos here, and do a little demo on row compression. Again, you can all download these notebooks and run them yourself in the database if you want. But I have a notebook here. Hopefully it's big enough everyone can read that. So I'm going to start just by showing you the data we have here. I have a database called parking tickets. I've used this data before. This is a data set from the city of Chicago. It is literally all the parking tickets that they wrote from the years 2003 to 2016. So there's like 38, 39 million tickets or something in there, and lots of columns, ticket numbers, license plate, what state it was from, car, make, and model, the time they got the ticket, where they were, what they were doing, how much the ticket was for, whether they paid it or not, etc. So we got some good general information there. And as I said, there's about 38 or 39 million rows in this table, which is an awesome data set to play with, but I want things to work a little faster. So I'm actually going to first start off and just take the top 100,000 rows and create a new table called Parking Tickets Mini, so that I have something a little smaller to work with, so we're not stuck here waiting around for compression operations to take place on millions of rows. So I went and created this table, have 100,000 rows. I'm going to run this query now that is just going to tell us how big uh, this mini table is. So I'm going to join some DMVs together and determine that this is a table of size 12.1 megabytes here. And I'll zoom in so you can see total megabytes is 12.133. So it's using a little over 12 megabytes to store those 100,000 rows. Okay, I'm going to now just apply row compression, right? I'm going to alter the table. I'm going to rebuild it with data compression equals row, which should be really fast because, again, it's a small amount of data. There we go, rebuilt in a quarter of a second. So now if I rerun that same query, you will see that we went from 12.1 megabytes to 10.9. So we saved just a little bit over a megabyte in optimizing the empty space in all the data types for that 100,000 rows. Okay, so not a non-trivial savings, especially when you consider how it would scale over millions and millions of rows, but some savings nonetheless. So now that we have this data that's been row compressed, I'm going to run a query here on sysdmdb database page allocations, which is a dynamic management function, and I'm going to get, pardon me, the first page that makes up this table. So this is going to actually return 2, and I'm not sure why it returns 2. I got to look into that at one of these days, but I know that the top value is going to work for me. And because I'm going to be running dbcc page here, I actually need a new query window because notebooks don't really play well with dbcc page, probably from the amount of data that it spits back at us. So hang on, let me scroll down. We copy this over to a new window so we can run it in a different window. And I need that number here, that first page. So what I'm going to do is I'm going to be running dbcc page. I need trace flag 3604. If you're not familiar with dbcc page, it's just literally going to read the data page from disk and print out the values for us so that we can see it in plain text. So I'm going to run this, and we have some buffer information, we have some page header information it's going to return, and then we're going to get down to the actual data that we have here. Now, the first thing I'm going to show you, and I will zoom in on for you here so you can see a little better. We have, you'll notice it says CD array. This is those column descriptors I was telling you about. So this is the array of column descriptors, which is showing us what the data type or how many bytes each column is for this particular record, right? So column 1 is a 3-byte short, column 2 is null, column 3 is a 2-byte short, 3-byte short, null, etc. So let's go down and look and see what that actually means. If I go down a little further here, all right, and I will zoom in, we have, so this is the actual data as it appears on disk, and this is it trying to render it as text for us. But you'll notice here, slot 0, column 1, offset 0 by 9, length 8, length physical 3. Right, so what this is saying is this is a column that is of type big int that would normally need 8 bytes, but the value we're storing here, which is this particular ticket number value, we only need 3 bytes to store that. So guess what? We get savings. So there's 5 bytes you just saved in that particular column in that particular row. Looks like the license plate number is null because this data set is not perfect. Because it's null, and I said earlier, null and 0 values take up no space. Right, so this is taking up 0 physical spaces. The state was New York, so the length 2 and the physical length is 2. No savings there. No savings on the car type as well. You'll notice some of these columns will give you savings, some of them will not. Here's the badge off number of the officer that wrote it, badge number 54. It's because of the text column, it says length 6, length physical 2. So it saved 4 bytes there in storing that value, just again by optimizing the storage of it. So that is just showing how you can look and see the actual savings from row compression on disk using dbcc page. Are there any questions, Kevin, if we have anything? I don't know if anything's popped up or not, but this would be a opportune time to take a moment if there was.
Yes, one question, two comments that deserve some thought. The question is, so with compression, is this data compressed everywhere, meaning pass over the network through TDS streams in the transaction log, etc.?
Is it compressed everywhere? I'm going to go with no. If you're querying over TDS, this is the fact that I'm querying it is not, the compression is transparent to that, right? As soon as it hits those access methods from where it is returned to the user, it's no longer compressed. Now, I believe you can enable TDS compression through other means, but turning on data compression isn't going to do that for you. As far as the transaction log goes, the values written to the transaction log, I believe, are the values that are written to disk. So I think the values might be compressed there, though I'm not exactly sure. I should look into that because that's a good question. And you said you had other comments?
Yeah, fair enough. There was a point here, I think in varchar that is stored off row, i.e. row overflow, is also not compressed via Unicode compression.
That's correct, yes.
And you might be able to add to the dbcc page statement with table results instead of setting the trace flag.
Yeah, I know you can do that. I kind of like how it looks here better. But yeah, that's a good trick. If you're in a position where you can't set trace flags or you don't want to for whatever reason, that's a excellent alternative.
Got another question here. What happens to an index? Is that compressed as well at the index row or page?
Okay, compression actually, and I haven't talked about this yet. I'll get to it in a little bit. So in that sense, this is a great question because it's coming up. Compression takes place at the partition level. So you can enable compression on an index, and it will affect all partitions of that index, or you can actually turn it on a specific partition. But if you compress one index, there is no saving of that fact, and it will not be inherited by other indexes for that table. So just because it's your, or if you have a table that's a heap or a table that has a clustered index on it, you compress the clustered index and you go and you create a non-clustered index, that's not going to be compressed unless you explicitly tell it to be.
Makes sense. Those were all the questions so far.
Awesome. All right. Well, in that case, we're gonna move right along here, and let me go back and talk about page compression now. Okay. So pull up my right thing here. So page compression kind of builds on row compression and will give you even better compression results in a lot of cases, not in all. But to think about, if I said row compression is kind of a storage optimization. Page compression is more along the lines of actual compression, and we'll see why when we go through how it works. So there's three components to page compression. First is number one, it will do row compression. So everything we just talked about will happen when you enable page compression, and then it will go through and perform column prefix compression and column dictionary compression. In order to do this prefix and this dictionary, we need some space in the data page, so it will create what's called a CI, or a compression information structure on each page. And it's important to point out that page compression may not be applied to every page, even though you have it enabled. SQL Server will once again try to be smart about this, and if it determines that there's not really any space savings that can achieved by using page compression, it may decide not to compress this page, but we'll go on and try to compress all the others. Also, page compression only applies to leaf level pages. So if we're looking here in the graphic of our very simplistic representation of a tree structure, the leaf level pages would be the ones at the bottom in light green. So any upper levels of the index will not have compression set with them. This would just be page compression, or those would just be the leaf pages rather. Sorry. Okay, so first we have prefix compression, page prefix compression. And what it's looking for is it's looking for a prefix in terms of byte values. And this makes it type agnostic, right? Because if we have, whether we're storing an integer value, a character value, if we have, var binary or something else that can be stored on disk, we're just looking at the binary data at this point. So data type doesn't really matter anymore. And what we're looking for is the largest, most common prefix. And we're actually going to take the longest value that has the largest, most common prefix, and that's going to be what's called our anchor record. And then we're going to translate all our other values to be stored in terms of that anchor value for their column. So if this is some data that we have, once again, this is hex data because we're talking about byte values. Our most common prefix would be 0, 1, 2, 3, 6, right? That is present in both. Now, even in this case, you'll notice one of them is 8 and 7, and then the rest is the same, FFB8. Even though everything else is the same, the prefix will only go as far until there's a value that differs between rows. So the fact that the rest of it matches doesn't matter here. Our longest, most common prefix is 0, 1, 2, 3, 6. Now I have this image here of basically trying to represent a data page. Once again, we have 3 columns and 3 rows in our page. We have a page header, and then we have that gray area, the compression information structure that I talked about. So what we're going to want to do is, first of all, we're going to want to figure out our anchor values. So we have our anchor row in the compression information structure that's going to store, and like I said, we're going to keep the longest value that has the common prefix for that column. So for the first column here, that would be AABBC, right? Our common prefix is AABB, and we want the longest value that has that prefix. So AABBC would be our anchor value for that column. For the second column, it's AACCBF, right? Longest value that has a prefix of AAC. And then the third one is going to be BCDFA, longest value with the common prefix. In this case, it would be BC, would be the common prefix. So these are our anchor values. Now what we're going to do is we're going to express every value on the page in terms of the anchor value for its column. So what that means is for the first column here, we have AABBC, and the first value is AABB, right? So we're matching the first 4 bytes of that anchor column. So instead of storing AABB, we can just store 4. right? And it will know to match the first 4 bytes of that anchor column. So that'll save us some space, right? That'll save us 3 bytes on that particular value because now it's just saying get the first 4 bytes of the anchor column. Awesome. The second row, CAB, well, that doesn't match anything at all, right? But we have to put it in terms of the anchor column. So what we're going to do is make it, because there's no match, we're going to make it 0 CAB. In other words, match the first 0 values of the anchor and then put CAB after that. Now notice this is actually larger. We didn't save space at all. We're consuming 1 byte more of space in this case. And then the third value is the anchor, right? It matches. So because of that, we're just going to store null. And we're not really storing null. We're storing a special pointer type of null, but it means, get the anchor value. So our um, our value we're storing here will take up no space at all, essentially, right? Awesome. So we're going to do the same thing for the other 2 columns now, right? AACCBF, that becomes null. AACC becomes the first 4 of the anchor value. AACDE will become 3DE because it's matching the first 3 of that anchor value, and then put a DE after it. BCDFA is another null. BCB will be 2B, the first 2 plus a B, and CAB matches nothing, so that will become 0 CAB again. So this is what the prefix compression has done, right? We've already achieved some savings on most of these values, and some others it actually takes a little more. So now that we've done prefix compression, we need to do dictionary compression. This is where the actual building of a dictionary of shared values comes, and some real savings, some more savings can be achieved in that way. So the way this works is it will deduplicate common byte values over all the columns of the page. It's not just limited to its column. It'll look across all the columns, create a zero-based array, which is the dictionary, and then if it has a match and there is a match in 2 or more columns, it will go ahead and create a dictionary entry and use a pointer to that dictionary entry instead of the value it's storing. So if we go back to where we left off, we're going to create our dictionary here. And the first value we can find that matches in 2 or more columns is the number 4, right? That's present in more than one column. So we'll put 4 in the dictionary. And now we'll just put a pointer here and say, go to index 0 of that dictionary. Second one here, 0 CAB, that will become index 1 in the dictionary. So now we've done the prefix compression and the dictionary compression on this page. And this is essentially what page compression will leave you with from where we started. Okay, now couple questions we'll get to about page compression here, or actually, well, I'll do this and then I'll do the demos real quick. The compression the CI structure, compression information with the dictionary and the anchor rows. This is rebuilt on an all or nothing basis. So if you update one row in your table or your index that has page compression on it, it's probably not going to rebuild it. But the structure has a page modification counter and it will keep track of the number of modifications. And then there's some thresholds that will trigger a rebuild for that page, right? So if there's more than 25 page modifications, or if the number of modifications is more than 25% of the number of rows on the page, then it will try to rebuild the structure. Does not guarantee it will actually succeed in rebuilding it. But if it does and it creates enough space for 5 or 25% more rows, then it will actually go ahead and go through with that rebuild operation. So with that, let's do another couple demos here. We'll go back to my notebook and we'll talk a little bit about page compression. So I'm going to work with that same mini data set we did before, but now I'm going to rebuild it all with page compression. And that should be pretty quick. Again, completed in half a second. Let's see how big that data is now if we run this query. So we'll see it is now 5.1 megabytes. So we went from like 12.1 to what, 10.9, and now we're at 5.1 with page compression. So we saved like 50%. We're taking up like half the space we did of the uncompressed version with page compression, which is pretty cool, I think. So once again, we're going to run that same query as before and get the top row of, or the first page of the table. Grab that page number and we'll plug it back into our other query here. And we'll take a look at what it looks like with page compression. Okay, run that. Yoink, here we go. So now we'll have a couple more things in our thing. We still have buffer information. We still have a page header. we get to this point now, and we have compression info. So this is our compression information part I told you about, and it's going to dump it all out in terms of raw bytes first. And so this is effectively the anchor values in the dictionary. So you'll notice we have some information that would seem pretty common if we're looking at car ticket information. We have, abbreviations of car makes: Chevy, Chrysler, Dodge, International, Kenworth, things like that that you would expect. We have some other values in here that I'll zoom in, just of some longer, very uh, common strings apparently, like impounded for unlawful drugs or improper city sticker display. That's something they love to get you with in Chicago. You'll also notice down here we have our page modification count that I was just telling you about. In this case, it's 0. No modifications have happened, but this is where it would actually keep track of the number of pages that have changed. So now if we go and we're going to see next, we have the dictionary structure it's dumping out, and breaking that out for us, we can see all the entries. I'm just scrolling down till we get to an actual data record. So here we go. Here's an actual row in the table at this point: compressed primary record. Again, we have the column descriptor array that we had before, but you'll notice there's a lot more nulls in there now because of the savings we're getting with page compression. So if we, and sorry, I keep zooming in and out on you here, but I promise it's for good reason. If we go now, we're going to go back to that same row we did before. So slot 1, length physical 3. Okay, it did not decide that this value was common enough that there could be savings that could be had here. Apparently, the state of New York is not something that could be derived from the anchor row. And I say that because we see length here is 2, but the physical length is 3. So it actually is taking up more space now, because remember, it's having to store that 0 that basically means do not use the anchor row for this. But if we go down to the next value here for a passenger license, that's apparently very common because that's now in the dictionary. And we can see that because we have length of 3, but physical length of 0. So that pointer that says, hey, go to the dictionary and get it from there, takes up no space. So we have some savings on some, we have some not savings on others, but overall the savings will outweigh the values that we don't get a savings for. So that's just very briefly looking at how page compression works physically. If you'd like to see, as I mentioned, page compression is actually occurs at the partition level. So if you were to query from sys.partitions, you could see all that. And actually, I'll run the second query here, which filters out the system objects. So we don't have to look through a couple hundred rows of things we don't care about. And we can see here we have parking tickets and parking tickets mini. Parking tickets mini has page compression deployed on its one partition, because I didn't put any explicit partitioning on this table, whereas there's no compression on the base table. If you'd like to see whether or not your database is using features that may require Enterprise Edition, there's a DMV for that. sysdmdb persisted skew features. Data compression is not an enterprise level feature anymore, but it still shows in this list. It has not been Enterprise Edition only since 2016 Service Pack 1, I believe, but it still shows here. There's also an estimation function you can use, SP estimate data compression savings, where if you're wondering if your data can be compressed well or not, this will go through, it will sample out 5% of the data in your table, basically by reading every 20th page, and then we'll try to compress that, and we'll give you the numbers back, which you can extrapolate and see, okay, would I really save space or not with either row or page or column store archive level compression, which we'll talk about a little bit. So with that, I guess I have another slide or two about page compression really quick here. So I'll do that, and then we'll get to some more questions. This is just showing the syntax, right? Page and row compression are both done at the create or the rebuild step, right? You add the with data compression equals none row or page value to that. You can do it at table creation time, index creation time, or you can alter either and do it that way. You can also do it at the partition level by specifying compression levels at specific partitions. So here I have with data compression equals row on partitions 1, and then page compression on partitions 2 to 6. You can set up things like that as well. And you can rebuild individual partitions and compress or uncompress them. As I mentioned before when I was answering questions, if you have a non-clustered index, those do not inherit any compression settings from the clustered index or heap. And when a clustered index is created or dropped, the result inherits the compression settings of the heap or the index. So if you have a clustered index and you drop it, and your table now becomes a heap, your records will still have the same compression setting they previously had. It's not going to go through and do that size of data operation to update all the records to a different compression type when it's building a different structure at all. So, oh, and then another thing people like to ask about, maybe I'm heading a question off at the pass here. How does compression play with TDE? The answer is actually very nicely. As I mentioned, you'll remember this slide where we talked about how compression occurs in the access methods. Well, if you're using transparent database encryption, your encryption takes place before the data is being written to disk. So what you're doing is you are encrypting data that is compressed. That works pretty well. That'll work just fine, actually. If you were to reverse the order of those two and try to compress data that has been encrypted, that will not work so well, right? Because encryption is taking data and removing patterns and effectively trying to make it look as random as possible, whereas compression is looking for these patterns and trying to reduce them and achieve savings for you. So the fact that TDE works only on disk actually makes compression and transparent database encryption incredibly compatible, and it's not uncommon at all to see the two of them used together. Backup compression, another thing to mention here. Backup compression is completely different from everything I just described to you. Backup compression is using a algorithm to compress the backup stream. Backup compression reads the values, well, backups in general read what's on disk and will write it out to a backup stream or a backup set of files or whatever. So if you have transparent database encryption enabled, and you're trying to use backup compression, you'll find that you won't get very good backup compression results at all, because it's that point it's trying to compress something that's been encrypted. Um, so it is definitely possible to use backup compression and data compression together. Those will work fine, but when you throw TDE into the mix, backup compression does not do well for you anymore. If you have deduplication in your hardware, or if you have, I guess that's on the next slide. So let's talk about, well, okay, hang on. Hold that thought for a minute. Certain things, as I mentioned, can't be compressed. Someone brought that up earlier. So system tables cannot be compressed. If you have binary or large object types that are not on a data or index page, those will not work with everything I just described to you. File streams can't be compressed, and varchar max can't be compressed either. How much space will you save? It depends. It is very much dependent on your data. Right, as I mentioned, there's a stored procedure that will estimate your data for you before you actually compress it and tell you if you can achieve any savings or not. Wow, I had a bunch of slides here I forgot about. Okay, data compression compatibility. As I mentioned, it was introduced in SQL Server 2008, and it became available in standard edition in SQL Server 2016 Service Pack 1. Um, Data compression cannot be used with sparse columns, though honestly, I have never encountered anyone who's ever used sparse columns. I don't know why they put that in there. Probably someone asked for it. But sparse columns use a completely different row structure, and that is different from the row structure that data compression uses. So if you're using sparse columns, you can't use data compression. But if you're actually using sparse columns, please tell me. I'd love to hear about it. When to use row or page compression? It's most effective on tables with high numbers of scans, or high tables that have a large percentage of read, or for data that is seldom accessed. I, for one, argue you can probably get away with using row compression all the time, especially because it uses a very, very trivial amount of CPU. Right, the CPU impact was less than 5%, and that was in 2008 on 2008 level hardware. I hope your hardware you're using now is way better than 2008 level hardware. So row compression should be no problem at all. Page compression should be trivial as well. And as I said, page compression is kind of intelligent to begin with. So it's not going to deploy that compression if it doesn't need it. And then finally, what I was going to mention earlier, what if my storage array does compression, right? What if I have a super awesome storage array loaded full of SSDs and pretty logos and flashy lights in the data center because we want a disco party in there, and we want, to know if we should use the storage array's compression or not. Again, you need to test this, right? Test it on your hardware with your data and your workloads. But chances are pretty good your storage array is going to do a better job than SQL Server does. And I say this because most storage arrays, especially the current ones, have really beefy CPUs that have lots of power for things like compression, and they can spend more time on that compression and get better compression than the algorithms I just showed you in SQL Server. Also, it's not going to be using your database server CPUs to do this work, right? Probably the biggest downsides to this is your data is no longer compressed in memory, and you're not transmitting compressed data over the wire anymore for your IO operations. But with a modern storage array, that shouldn't be an issue either anyway. And then finally, as I mentioned, with deduplication, if your super cool storage array also does deduplication, you might not want to use rower page compression at all because it's going to be able to deduplicate things much more effectively if it's not having to work around the compression methods we already discussed. So with that, are there any other questions about page compression or anything else I've talked to this point?
Yes, there are a couple of questions, a couple of comments in chat here.
Okay.
The first one is, let's say you started out and used row level compression for an index, and then you decided, I'd like to make this page level compressed. Would the row be reworked during this page conversion, or does it just stay where it is?
At that point, it's going to rewrite the whole object, right? Because you're doing a rebuild to change the compression type. So it's basically going to build a whole new structure. So I don't think it's going to like take the row values that you've already done and keep them the same. It's going to rebuild it all anyway. It should arrive at the same output, of course, but I don't think it's going to save it at that point because rebuild by definition means give me a whole new structure.
Makes sense. So no problem with TDE, but how does compression work with always encrypted? Are there any issues there?
I am not qualified to talk about that because I've never worked with always encrypted. My thought is that always encrypted does that. I believe that exists on disk, but again, I can't address that because I've never dealt with that. So sorry.
Yeah, given that it's encrypted binary data stored on disk, I would probably say you would not want to compress objects that are using always encrypted.
Okay, fair enough.
But that's my guess.
Yeah.
So there was a use case for sparse, and comment in chat here. Sparse came out one version prior to data compression, so it was helpful for that one version if you had large tables with a lot of nulls on them.
I would say you needed like lots of columns, or I think you could have lots of columns, right? Couldn't you have like 100 times the number of columns or something stupid if you had sparse enabled? So I didn't realize was that a 2005 feature then? I guess I didn't realize that.
Yeah,
So
yeah.
okay,
So
fair
sparse
enough.
was in 2005, and yes, you're right. You could have ridiculous numbers of columns on tables that probably should never have.
Yeah, I think
Definitely
like
should never have.
30,000 or something like that.
Yep. But if you did
Yeah,
have a huge number of nulls, it didn't save the null byte for every
yeah,
row, for every
I remember
column.
that was like the one selling point of it or whatever. So
Yeah, but nowadays, no, no use for it. In varchar max, data stored in row can be page compressed, and the specification there is in row.
yes, but I believe most of it is not going to be in row. So that seems like a not common scenario would be my guess.
Makes sense, yeah. Um, that was all of the questions and comments that we've got so far.
Awesome, cool. All right, excellent. And we're doing pretty good on time. We got enough time here. We can finish up strong with some column store compression, right? Let's talk about the newer hotness than rower page compression, right? I still love row and page compression, but we need to talk about some column store too. So column store has, of course, changed a lot over the years. It was introduced in SQL Server 2012. At that point, it was for non-clustered indexes only, and it was read only, so you couldn't update it at all, and it only worked in Enterprise Edition. So if you wanted to deploy a column store index and you had data that was updated, you had to drop and rebuild the column store index, which was not really cool, but that's what you had to work with in 2012. Then in 2014, they made clustered column store indexes available, and they were updatable. That was still Enterprise Edition only. In 2016, they gave you updatable non-clustered column store indexes, and you could create secondary indexes that were regular B-tree indexes, and they made it available in Standard Edition after Service Pack 1, which was pretty darn cool. In 2017, they added adaptive query processing, so you could dynamically choose, your type of physical join based on row counts, and you could add computed columns to the clustered column store indexes if you wanted. And then in 2019, they gave us online building and rebuilding of clustered column store indexes. So they've come a long way from something that I remember when it was first introduced in 2012. It was kind of like okay, how am I actually going to make this useful, to something that can be pretty darn useful depending on what you're doing. But to talk about the internals of that, so if we have a relational table, a row store table, no column store here, and I represent it by this square, to break it up as a column store, well, we're going to be breaking it up not only into columns, but we're going to slice that table up into what are called row groups, right? Groups of rows, and then we're going to slice those row groups up into columns. So a row group is usually about 1,000,000 rows, actually 1,048,576 rows, or one row for each byte in a megabyte, so 2 to the 10th power of rows. We slice it up into these row groups and then into columns on that. And then on top of the actual column store here, we have, well, each one of those is referred to as a segment, right? So a particular column of a row group is a segment. On top of that, we also have delta row groups, which there may not necessarily be one delta row group per row group, but there can be more than one delta row group per column store. And these are clustered indexes. These store information about new rows or updated rows that were in the column store and are changing, or that have not been added to the column store yet, and also keeps track of rows that have been deleted from the column store. So we don't need to update the column store structure because we actually can't update the column store structure with any queries that we write. And then take those delta row groups together. Those are known as the delta store. And then on top of that, we have a process called the tuple mover, which will then take and update the particular row groups with the changes reflected in the delta store. So we have a bunch of moving parts going on in the column store here. And this could be probably a presentation on its own. But what I'm really here to talk about tonight briefly is the compression algorithms present in column store. And there's a bunch of them. So there's several algorithms possible. You do not get to pick. It's going to work through the data and use its own telemetry and profile of the data to determine what is going to be the best result for you. So you don't get control over this, but we can see what kind of compression algorithms are available. This may not be an exhaustive list. These are all the ones I have been able to find out about and extract from different people in key locations who would know. But officially, column store compression algorithms are more or less a black box. So the first one we're going to talk about is called value-based encoding or value scale, and this is pretty cool because what it's doing is it's actually creating a mathematical relationship between a value and what would be stored for that value. So let's say we have a column that is of type integer, and we have 5 rows in that column. So these are our values here. And if we profile that data very quickly, we'll see that we have a minimum value of 1105 and a max of 1122, and we would need 11 bits to store these values just based on the number of bits necessary to store that value. Okay, if we were to say, okay, we're going to scale this, and what we're going to do is we're going to subtract the minimum. So we're going to subtract 1105 from each of those values, and we're going to store the result. So now we're storing, 0, 4, 17, 8, and 2. We have a minimum of 0, a maximum of 17, and we need 5 bits to store those values instead. So all we would do then is add our base value of 1105 to the stored values, and we'd get back what we started with. But we saved, in this case, 6 bits per row, which, can add up significantly over millions or billions of rows. This type of compression only works for integer types, and it does not have to be subtraction. It can be a more complex mathematical relationship, but subtraction's really easy and works good for a demo explanation like this. So figure out what the minimum or a base value would be. Figure out a relatively simple mathematical operation or something more complex that can get us the maximum savings that way, and store then these smaller values that take up less space. That is value scale. The next option is called bit array, and what this will do is create a bit column for each distinct value. So if we have something like blood type groups, right? There's only 4 major blood groups. So what we could do is we could actually create a bit column for each, and then just set the bit in the column that was the value that we're trying to store, right? If you have a couple distinct values, this will probably work great. If you have lots of distinct values, your results may vary, may not be as good. But if you're doing something like a predicate search and you're looking for what values are present in this table, well, we can very quickly tell that because we have them in a column now, right? We don't even have to scan to figure it out. We just have this information present. And then you can, join these columns with bit masks and get your results that way. So this could be, if you have a limited number, this might be what's chosen. Again, with the dictionaries, like we've talked about earlier, we have a couple different ways we can do what are called dictionary encodings, where we build a dictionary of our distinct values and replace the data with these dictionary values instead. So going back to our car tickets again, let's say we're doing vehicle makes now, right? So we have some Chevy, Ford, Audi, Tesla, etc. If we build a dictionary of this, we would have a dictionary 0, 1, 2, 3, right? Chevy, Ford, Audi, Tesla, and then just store that dictionary ID, right? Kind of like creating a lookup table that we do in a database. As an added bonus, those dictionary IDs are always going to be an integer value, which means we'll save space that way as well. We won't actually have to store the strings repeatedly, and we can have the smallest possible integer value. We can take it a step further, perhaps with Huffman encoding, which I mentioned earlier, and make the most common value the smallest. So, Chevy might be the most popular one. It would get the smallest value, followed by Ford, Audi, Tesla, etc. Right. Next. Oh, and then okay. So I mentioned the Huffman coding here. Yeah, it can be made more optimal with that, depending on how prevalent your values are. Next, we have run length encoding, and this will get rid of repetition by grouping values together, provided they occur next to each other. So what I mean here is, let's say we're doing colors. We have red and blue. If we have the data sorted and there's 105 reds followed by 92 blues, well, I don't need to store the value red 105 times. I don't need to store some dictionary value for red 105 times either. I could do something much simpler and say, hey, run length encoding, the first 105 values are red, the next 92 are blue, right? You can save a ton of space this way because we're not repeating the values at all at this point, right? This can become less efficient though, depending on your ordering. So if we start having, alternating red and blue values, well, now our run length encoding table becomes a little bigger and we have more repetition in that as well. So that may affect how awesome it could be. And then you can also combine this with dictionary encoding and once again, build a dictionary and have IDs there and then do it that way. So you can get additional savings that way. So that is just the column store compression methods I know about. And to very quickly go through this and actually shoot. Okay, I have my notebook here on column store compression. I actually need to build the column store, and that's going to take about 90 seconds. So what I'm going to do is I'm going to kick off this column store build. And while it's doing that, I'm going to cover the rest of these slides, and then we'll come back and play with the demo real quick. So just to talk about column store compression syntax, right? If we're creating a clustered or non-clustered column store index, the syntax is literally create clustered column store index. You get a table, you get a compression type you can pick here too. Column store, which is the default, or there is column store archive, which will perform column store compression and then do a second layer of compression on top of it all to save you even more space. It's a proprietary algorithm. I don't know what it is. This is generative column store archive was designed for very infrequently accessed data that you want to store in a column store. So here it mentions it. And yeah, it might be some sort of modified LZ77 compression, but we're not sure. When should column store be used? If you have queries that scan large amounts of data, especially on really big tables, column store might help you. If you have lots of repetitive values in a data set, if you have data warehousing type workloads, if you're trying to do real-time analysis on OLTP workloads, these are all great cases for when you would want to use column store, when your workload might see a benefit from it. Again, test with your data and your workload on your hardware. I can't repeat that enough, but as a consultant, I all the time had to tell people to do this and walk them through that or do it for them because that's the only way you're really going to know if it works well or not. When should you avoid column store? On small tables, and by small I mean under 1 million rows. It will not benefit from the column compression because it won't be stored as a segment because it's trying to group things in that 2 to the 10th power number of rows. If you have columns containing really, really unique strings that won't compress well with any of the methods we talked about, you probably won't see a benefit from Columnstore compression. If you do lots of queries that return all the rows in a table, you're not going to get your data back any faster with a column store index generally, or tables that are updated very frequently, because then you'll be working off the Delta store all the time anyway, and that isn't really going to help you. And to finally hit home, column store indexes aren't just going to make things better, right? As a consultant, I can't tell you how many places I walked into where they were having query performance train wrecks, and one of the first things they'd say to me was, "Well, we created a column store index on it." Well, that's great. Do you actually know why you created a column store index, or were you just kind of hoping magic would take your problem away? Column store indexes are not a panacea. They might make things better in the wrong situations, or they might make them worse. So this is definitely something to think about what you're doing before you just go creating a column store index on it. And please test. All right, so to come back to our demo here, we have built our column store index. And we're going to look at some of the very quick internals queries that you can run on a column store index. Hang on, I'm closing this other window. So there is a DMV called sys.columnStoreRowGroups. This will show you the number of row groups in, and we remember we told you we had about 37 million rows in this table. Well, there's about 37 rows here. So you'll notice, and I'll scroll down and I'll zoom in so you can see these are all compressed, which means they are in a column store format. They all have 1,048,576 rows until we get to the last couple where some of them are a little smaller. But it is literally building out these row groups with that many rows. What happens if we add a row to the table, right? So I'm going to take this column store index table now, and I'm going to insert a new row into it, right? Just a good old insert into with some values here. There, I added a row. Now we're going to requery that and look and see what we have. And I'm going to scroll down and zoom in again and show you. So if we zoom in here, you'll notice we still have all these compressed rows. We have this last row, which is open. It's not compressed, and what that means is it is not in a column store format. It is actually in the Delta store in a B tree, and it has this column over here is the hopped ID. So this particular one row is sitting in a B tree with that hopped ID, and until we rebuild the table or until the tuple mover gets triggered and has to run, it will be sitting in a B tree in a row store index instead of in the column store. Very quickly, we can look at the segments that are in the column store index. There's a DMV for this too, sys column store segments. And this will show us basically every segment in the table, right? There's 222. This is for the 5 columns in the table and the 37 row stores. It'll show you every segment. I am live. All right. Thank you all for your patience. My microphone has a little mute button on the line here, which is great, but sometimes that gets out of sync with everything else, and no matter what I do, I can't talk. So my apologies for all that. Let me reshare my screen here, and I will finish up what I was talking about. What was I talking about? I was talking about looking at the different segments. Is my screen visible now?
Yes.
Okay, awesome. So here we have literally a list of every different segment, which is, remember this particular table has 5 columns, I believe, 6 columns, and there's 37 row sets, so that times that is apparently 222. But it will show you each segment, and it will show you the column, the row, and what the encoding is, right? What method it's using. So that is apparently using method number 5. There we go. Hit escape, get out of that. So you can look and see what segments are using what. What I'm going to do is I'm actually going to skip down here, and we're going to look at. I'm actually going to go. Okay, so I have here. So 5 is string store by value based. So that is a string binary storage that's being used with no dictionary for that particular case. But the really cool one I was going to show you is, and hang on, why is that? There we go. I'm just going to show you real quick. So I've been using DBCC page, right? That was what all the other demos were were based on, there's another one for Columnstore indexes, and it's actually called DBCC CS index for Columnstore index. So if you're trying to, if you want to look at the internals of your Columnstore index, you can do it this way. You got to give it a database name, a hopped ID, column segment ID, so you know what you're looking at. But hang on here, let me pull one of those up real quick, and we can try this and see. Here we go. So here's a hopped ID. I'm going to plug that in, and we will see if this works or not. But this should show us column number 3, which is the license type that they have. Here we go. So what we have here is, notice it looks very different than looking at a row store. But what we actually have, if we zoom in, we'll see it says RLE header. So this is using run length encoding. And what it's doing is it's figuring out, okay, run length index 0, it's the value 20, and there's 823,000 rows that are using that value 20. So and then it's going to go 65, 45. Notice how it's in order of decreasing prevalence, more or less, is what it's doing here. But this is actually using run length encoding for the license type, which is a char3 value. And it does not have the key for that in this particular structure that I'm looking at. But just to show you, this is how it would actually break it up and display that for you. And I have some other queries you can go ahead and run in here if you want. Again, this is all downloadable. But that is really the last part I wanted to show you of Columnstore demos. My apologies again for choking and muting myself. But so we talked about when should Columnstore be used, when should it be avoided. That is the end of my material, so I'm going to back up here. There's some great resources on compression and index internals. I have some links here. Jonathan Kahayas, Sanjay Mishra, Microsoft Certified Master Readiness videos has information. Nico Negebauer has a ton of information on Columnstore. He's got like over 200 blog posts on different aspects of Columnstore. So if you really want to learn Columnstore, read his stuff. And if you want my materials from this session, and I have it again here at the bottom of this slide, go to bobpusateri.com/r/compression. That will take you to the GitHub repository for this session, so you can get the slides, you can get the demos, you can get links to all those materials. So with that, if anyone has any questions for the end, I'll be happy to take them.
Yes, there were a couple of questions in here. One of them, if you have multiple indexes on a table that are filtered, say you've got date partitions, would it be possible to have one be compressed, thinking of archiving strategy versus having live months be non-compressed?
My first thought is I believe that's possible through the partitioning. I think it would allow that. I've never tried that, but I would be surprised if it didn't work. Would be my thought.
All right, and another question. Is there a cardinality type sweet spot for compression usage?
Off the top of my head, no. But that sounds like something I would want to do some more academic style research on before I venture to guess on that.
Fair enough. If there are any other questions from chat, now is your last opportunity to do it for the evening. So get typing, get your questions in, and let's ask Bob. You've just stumped him. So
you can stump me. I'm not hard to stump, believe me.
You had some great answers throughout. So there are any more answers that you'd like? Questions? By the way, you did a super job, says Mark in chat.
Thank you very much, Mark. Hope you all enjoyed it.
Yeah, so it looks like no more questions. Plenty of kudos.
Awesome. Well, thank you all for sitting through this and listening to me hack away over here. And yeah, hope you enjoyed it. And look forward to presenting in person again sometime. But in the meantime, I'm glad I have virtual opportunities like this to get together and talk with people.
Absolutely. We were absolutely glad to have you here. Appreciate you getting into this talk on compression. Definitely a lot deeper than normally would see with compression. So we certainly appreciate that.
Awesome.
And with that, we are going to wrap up tonight's edition of the Triangle Area SQL Server User Group's Advanced DBA subgroup. So everybody have a wonderful evening, and hopefully we'll catch you again next week where Kathy Kellenberger is going to be presenting for our main meeting. So until then, everybody take care.